Introduction. Students, look at this structure. Does anyone know what is this?
Sir, this is a benzene ring.
Correct, a benzene ring. And now, who will define aromatic hydrocarbons?
Sir, aromatic hydrocarbons are those which contain one or more benzene rings.
Very good, Rahul. Today we will learn about aromatic hydrocarbons. Come, let's start. Objectives. At the end of this lesson, you will be able to explain aromatic hydrocarbons, recognize and write structures of isomers of aromatic hydrocarbons, comprehend the structure of benzene, explain aromaticity, understand mechanism of electrophilic substitution reactions of benzene, predict the directive influence of substituents in monosubstituted benzene ring, learn about carcinogenicity and toxicity. Aromatic hydrocarbons. Aromatic compounds are a class of hydrocarbons that possess much greater stability than their conjugated unsaturated system suggests. The simplest example of this class of compounds, benzene, was isolated from illuminating gas by Michael Faraday in 1825. In the years to follow, this compound and homologues were isolated by the distillation of resin gums from balsam trees. Because many of the resin gums had fragrant aromas, these compounds were often called aromatic compounds or aromatic hydrocarbons and are also known as arenes. In 1845, August von Hofmann isolated benzene from coal tar. This isolation method remained the chief source of benzene until 1950s. Today, most benzene is produced from petroleum. Simple aromatic hydrocarbons come from two main sources, coal and petroleum. Coal is a complex mixture of a large number of compounds, most of which are long-chain compounds. If coal is heated to about 1000 degrees Celsius in the absence of air or oxygen, volatile components, the so-called tar oil, are stripped out. By fractional distillation, benzene, toluene, xylene, and naphthalene as well as many other aromatic compounds are obtained. Isomerism. In benzene, all 6 hydrogen atoms are equivalent, so it forms one and only one type of monosubstituted product. When 2 hydrogen atoms in benzene are replaced by 2 similar or different monovalent atoms or groups, then 3 different position isomers are possible. First one is 1, 2 or 1, 6, known as the ortho. Second one is 1, 3 or 1, 5 as meta. And the third one is 1, 4, known as para, disubstituted compounds. Nomenclature. Naming aromatic compounds isn't quite so straightforward as naming chain compounds. Often more than one name is acceptable, and it's not uncommon to find the old names still in use as well. The benzene ring. All aromatic compounds are based on benzene, C6H6, which has a ring of 6 carbon atoms and has this symbol. Each corner of the hexagon has a carbon atom with a hydrogen attached. A. The benzene ring is named as a phenyl group when it is a substituent. B. Multiple substituents on a benzene ring are numbered to give these substituents the lowest possible numbers. When only 2 substituents are attached to a benzene ring, they can be named by the common nomenclature using ortho, O-, 1 to 2 placement, meta, M-, 1 to 3 placement, or para P-, 1 to 4 placement. Given compound is 1-ethyl 2-methylbenzene O-methyl-ethylbenzene. Can you name the given compound? It is 1-ethanyl 3-methylbenzene M-methyl-ethanyl-benzene. Nomenclature of alkenes 2. C. Some common names involving benzene rings that you should know are toluene and orthoxylene. Biphenyl. Notice the numbering convention for this compound. D. Polycyclic aromatic hydrocarbons that you should know are naphthalene. A common nomenclature if only one substituent is on the naphthalene ring system involves the use of alpha and beta. E. The annulenes are large aromatic rings that have 4N plus 2p electrons in a cyclic conjugated system. That is, N is equal to any whole number including 0. The compound 1, 3, 5, 7 cyclooctatetraene is not an annuline. It has 8 p electrons which would yield 1.5 for N. Structure of 10-annuline. Structure of benzene. A chemist, Kekule, in 1865 suggested the following structure for benzene. According to Kekule, 6 carbon atoms in benzene are on the 6 corners of a regular hexagon. Each C atom is attached with one H atom. There are 3 alternate double bonds between 2 C atoms to complete 4th vacancy of carbon. There was an objection to the above-mentioned structure of benzene that it must give 2 orthoisomers, di-substitution, but in actual practice, only one orthoisomer is obtained. To answer this question, Kekule extended his theory and argued that the position of double bond in benzene is not fixed, but the double bond system is revolving over the hexagonal ring. He proposed the given structures and said that all C-C positions have a partial double bond character. In the extension of his theory, Kekule explained that C atoms in benzene were in a state of vibration, and due to this vibration, each pair of C atoms has a single bond half of the time and a double bond the other half of the time. Kekule's structure failed to explain why benzene with 3 double bonds does not undergo addition reactions like alkenes or alkynes. Resonance 1. Modern instrumental studies confirm earlier experimental data that all the bonds in benzene are of equal length, approximately 1.40
picometer.
1
Picometer
equals 1 into 10 raised to the power minus 12 meter. This bond length falls exactly halfway between the length of a carbon-carbon single bond, 1.46
picometer,
and a carbon-carbon double bond, 1.34
picometer.
In addition, these studies confirm that all bond angles are equal, 120 degrees, and that the benzene molecule has a planar or flat structure. Modern descriptions of the benzene structure combine resonance theory with molecular orbital theory. Resonance theory postulates that when more than one structure can be drawn from the same molecule, none of the drawn structure is the correct structure. The true structure is a hybrid of all the drawn structures and is more stable than any of them. The greater the number of structures that can be drawn from a molecule, the more stable the hybrid structure will be. the difference between the calculated energy for a drawn structure and the actual energy of a hybrid structure is called the resonance energy. The greater the resonance energy of a compound, the more stable the compound. The two Kekulé structures that can be drawn from the benzene molecule are actually two resonance structures. The hybrid of these structures would be drawn as this, where the circle represents the movement of the electrons throughout the entire molecule. This delocalization of pi electrons found in pi molecular orbitals, is also found in conjugated diene systems. Like benzene, the conjugated diene systems show increased stability. Because of resonance, the benzene molecule is more stable than its 1,3,5 cyclohexatriene structure suggests. This extra stability, 36 kilocalories per mole, is referred to as its resonance energy. Orbital picture of benzene. Because experimental data shows that the benzene molecule is planar, that all carbon atoms bond to 3 other atoms, and that all bond angles are 120 degrees, the benzene molecule must possess sp2 hybridization. With sp2 hybridization, each carbon atom has an unhybridized atomic p orbital associated with it. The overlap of the sp2 hybrid orbitals would create the sigma bonds that hold the ring together, while the side-to-side overlap of the atomic p orbitals can occur in both directions, leading to complete delocalization in the pi system. This complete delocalization adds great stability to the molecule. Molecular orbital theory predicts that overlapping 6 atomic p orbitals will lead to the generation of 6 pi molecular orbitals. 3 of these pi molecular orbitals will be bonding orbitals, while the other 3 will be anti-bonding orbitals, as shown in the figure. The 3 low-energy orbitals denoted pi1, pi2 and pi3 are bonding combinations, and the 3 high-energy orbitals denoted pi4, pi5 and pi6 are anti-bonding orbitals. 2 of the bonding orbitals, pi2 and pi3, have the same energy, as do the anti-bonding orbitals pi4 and pi5. Such orbitals are said to be degenerate. Because the electrons are all located in bonding orbitals, the molecule is very stable. Additional stability occurs because all the bonding orbitals are filled and all the pi electrons have paired spins. Molecules that possess all these characteristics are said to have a closed bond shell of delocalized pi electrons. Molecules such as benzene that possess a closed bond shell of delocalized pi electrons are extremely stable and show great resonance energies. Aromaticity. Aromaticity is a property of conjugated cycloalkenes in which the stabilization of the molecule is strong due to the ability of the electrons in the p orbitals to delocalize and act as a framework to create a planar molecule. The 3 general requirements for a compound to be aromatic are: 1. The compound must be cyclic. 2. Each element within the ring must have a p orbital that is perpendicular to the ring, hence the molecule is planar. 3. The compound must follow Huckel's rule. The ring has to contain 4n plus 2 p orbital electrons. Among the many distinctive features of benzene, its aromaticity is the major contributor to why it is so unreactive. The delocalization of the p orbital carbons on the sp2 hybridized carbons is what gives the aromatic qualities of benzene. Preparation of benzene by the decarboxylation of sodium benzoate. This method is used in the laboratory to obtain benzene. Sodium benzoate is heated with soda lime, and when it gets decarboxylated, that is, removal of carbon dioxide, benzene is obtained. By heating phenol with zinc. When phenol vapors are passed over heated zinc dust, benzene is formed. By polymerization of ethine, acetylene. When ethine or acetylene is passed through a red-hot copper tube, it polymerizes to benzene. By the hydrolysis of sulfonic acid. Benzene sulfonic acid on hydrolysis with superheated steam gives benzene. Physical properties. Aromatic hydrocarbons are non-polar molecules. They are usually colorless liquids or solids. The naphthalene balls are used in toilets and for preservation of clothes because they have unique smell and the moth-repellent property. Aromatic hydrocarbons burn with sooty flame. They are immiscible with water but are readily miscible with organic solvents. Chemical properties 1. Although aromatic compounds have multiple double bonds, these compounds do not undergo addition reactions. Their lack of reactivity toward addition reactions is due to the great stability of the ring systems that result from complete pi-electron delocalization, resonance. Aromatic compounds react by electrophilic aromatic substitution reactions, in which the aromaticity of the ring system is preserved. For example, benzene reacts with bromine to form bromobenzene. The bromination of benzene. All electrophilic aromatic substitution reactions share a common mechanism. This mechanism consists of a series of steps. An electrophile, an electron-seeking reagent, is generated. For the bromination of benzene reaction, the electrophile is the Br plus ion generated by the reaction of the bromine molecule with ferric bromide, a Lewis acid. The electrophile attacks the pi electron system of the benzene ring to form a non-aromatic carbocation. The positive charge on the carbocation that is formed is delocalized throughout the molecule. The aromaticity is restored by the loss of a proton from the atom to which the bromine atom, the electrophile, has bonded. Finally, the proton reacts with the FeBr4- to regenerate the FeBr3 catalyst and form the product HBr. You can summarize this particular electrophilic aromatic substitution mechanism like this. Chemical properties 2. In another example of an electrophilic aromatic substitution reaction, benzene reacts with a mixture of concentrated nitric and sulfuric acids to create nitrobenzene. The reaction of benzene with concentrated sulfuric acid at room temperature produces benzene sulfonic acid. When benzene is treated with an alkyl halide in the presence of anhydrous aluminium chloride, alkyl benene is formed. This reaction is known as Friedel-Crafts alkylation reaction. The reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acid, AlCl3, yields acyl benzene. This reaction is known as Friedel-Crafts acylation reaction. Directive influence of a functional group in monosubstituted benzene 1. A monosubstituted benzene, when treated with an electrophile, could undergo 3 electrophilic aromatic substitution reactions. Each reaction yields a disubstituted benzene as the organic product, which can be identified using the descriptors ortho, meta, and para. A is equal to any substituent. E plus is equal to electrophile. If the relative yield of the ortho product and that of the para product are higher than that of the meta product, the substituent on the benzene ring in the mono-substituted benzene is called an ortho-para directing group. If the opposite is observed, the substituent is called a meta-directing group. Look at this example. We can see that the methyl group is an ortho-para directing group. Directive influence of a functional group in mono-substituted benzene 2. If electrophilic aromatic substitution of a mono-substituted benzene is faster than that of benzene under identical conditions, the substituent of the mono-substituted benzene is called an activating group. Under identical conditions, reaction 2 is faster than reaction 1. Thus, the methyl group is an activating group. All activating groups are electron-donating groups. Common activating groups are if electrophilic aromatic substitution of a mono-substituted benzene is slower than that of benzene under identical conditions, the substituent in the mono-substituted benzene is called a deactivating group. Under identical conditions, reaction 2 is slower than reaction 1. Thus, the nitro group is a deactivating group. All deactivating groups are electron-withdrawing groups. Common deactivating groups are carcinogenicity and toxicity. Benzene and polynuclear hydrocarbons which have 2 or more benzene rings fused together are toxic and possess carcinogenic or cancer-producing properties. Incomplete combustion of organic materials like tobacco, coal and petroleum leads to the formation of such polynuclear hydrocarbons. Cancer is caused when they enter the human body and undergo biochemical reactions and damage the DNA. Some of the carcinogenic hydrocarbons are Did you know? Benzene was first discovered by Michael Faraday in 1825, who called it bicarbonate of hydrogen. In 1833, it was discovered again by Eilhard Mitzelrich, who distilled it from gum benzoin. That's how it gets its name. Since it dissolves many organic and greasy substances, benzene found widespread use in removing paint and organic stains from metal surfaces. In 1849, Charles Mansfield perfected a method for extracting benzene from coal tar on industrial scales. Summary. Let us summarize what we have learned. Aromatic hydrocarbons, despite having unsaturation, undergo mainly electrophilic substitution reactions. These undergo addition reactions only under special conditions. Benzene and benzenoid compounds show aromatic character. Aromaticity, the property of being aromatic, is possessed by compounds having specific electronic structure characterized by Huckel's rule, 4n plus 2 pi electron rule. The nature of groups or substituents attached to benzene ring is responsible for activation or deactivation of the benzene ring towards further electrophilic substitution and also for orientation of the incoming group. Some of the polynuclear hydrocarbons having fused benzene ring system have carcinogenic property.